Northern Plains Territory, winter of 1865. While neighboring Lakota families erected standard buffalo hide tipis before the first snow, Hunter Redman was still gathering materials in his 8th week, building a shelter with an inner hide curtain that consumed twice the hides. His fellow hunters called it wasteful. The tribal elders shook their heads. Why use extra hides when standard tipis had worked for generations? Then the unprecedented winter arrived. Temperatures dropped to 40 below zero with 70-mile-per-hour winds that would test every shelter on the northern plains. Standard tipis suffered partial collapse and interior frost. Families huddled in near-freezing conditions, burning through fuel supplies. But Redman's inner liner system maintained steady warmth, using 30% less fuel while sheltering 12 people through the worst storm in living memory. What did this Lakota hunter understand about heat circulation and moisture control that accepted tribal wisdom had overlooked? Redman crouched beside the Niobrara River in the pre-dawn darkness of November 20th, 1865, examining buffalo hides by firelight with the methodical attention of a man who had learned that winter preparations could mean the difference between survival and death. At 42, he carried the weathered confidence of someone who had endured 25 northern plains winters, but his scarred hands moved with unusual urgency as he selected each hide for thickness and flexibility. The memory of his near-fatal night in 1840, when his family's teepee collapsed under wind and his 16-year-old body had pressed against his dying brother under frozen robes, drove every decision he made about shelter. The standard method employed by every family in their winter camp followed patterns refined across generations. Lodge poles of 22 feet in length formed the familiar 18-foot diameter circle, with 17 additional poles secured against the primary tripod to create the cone structure that had housed Lakota families since the earliest memories of the elders. 18 buffalo hides, each roughly 4 millimeters thick, were sewn together in the traditional overlapping pattern and stretched directly against the inner face of the poles. The smoke flap arrangement at the apex allowed ventilation, while the eastern-facing door followed the ancient protocol for greeting the morning sun. Floor coverings consisted of hide mats laid directly on the ground, typically 1 or 2 layers thick, with buffalo robes providing additional insulation for sleeping. Redman had observed this system's limitations with the same careful attention he applied to tracking game. During 3 previous winters, he had measured interior temperatures with a trader's mercury thermometer, recording how frost formed consistently on inner wall surfaces when outside temperatures dropped below zero. He had counted fuel consumption, noting that neighboring families required 40 to 50 bundles of dried buffalo dung daily to maintain barely adequate heat. Most troubling, he had watched condensation from breath and cooking fires freeze against the hide walls, creating ice formations that reduced the hide's insulating properties and created cold spots that drew heat from the living space. His solution emerged from knowledge gathered during a trading expedition to Blackfeet territory in 1862. An elder named Running Wind had shown him a modification that seemed wasteful at first glance, but revealed sophisticated understanding of heat flow and moisture control. The concept required an inner hide curtain suspended several inches away from the outer tipi wall, creating an air gap that would serve multiple functions simultaneously. Redman had spent 3 years refining the measurements and installation method, calculating that the modification would require approximately 6 additional buffalo hides sewn into a continuous liner panel 16 feet high and 24 feet in circumference. The technical requirements demanded precise execution. The liner needed suspension at 14 feet above ground level, roughly 10 inches below the apex where the lodge poles converged. Buffalo sinew rope, totaling 45 feet in length, would secure the liner at multiple attachment points to prevent sagging or contact with the outer wall. The critical measurement was the air gap itself. 4 to 6 inches of separation between liner and outer cover around the entire circumference. This gap had to remain consistent from ground level to the smoke hole opening, requiring careful tensioning of the suspension system. Redman understood that the bottom edge of the liner presented the most challenging installation problem. Standard practice would allow the liner to hang freely, but his observations of heat flow convinced him that the bottom required sealing to prevent drafts from entering the living space directly. His method involved folding the liner's bottom edge under itself and overlapping it with floor hide mats by 6 inches, creating an air seal while allowing controlled airflow beneath the outer wall. Between the outer cover and liner, he planned to stuff dry prairie grass in a 2-inch thick layer, providing additional insulation and moisture absorption. The material costs reflected the system's apparent wastefulness. Where a standard Tipi required 15 to 18 hides for covering plus 3 to 4 hides for floor mats, Redman's modification demanded 6 additional hides for the liner, plus extra sinew for suspension, plus the labor time of 2 adults working 3 full days for installation. In terms of trade value, the extra hides represented roughly the cost of 1 trade gun, a significant investment that most families would consider better applied to winter provisions or tools. His wife, White Cloud, supported the project despite its social costs, partly because she had witnessed his systematic approach to winter preparation over their 18 years of marriage. She had seen him track temperature variations, measure fuel consumption, and modify equipment based on observed performance rather than inherited tradition. When he explained that the air gap would create a convection current that carried moisture-laden air upward and out through the smoke hole while preventing cold transfer through the walls, she recognized the logic, even if the execution seemed extravagant. The social resistance began immediately. Elder Sitting Bear, whose 68 years of experience commanded respect throughout their band, questioned the wisdom of altering methods that had sustained their people through countless winters. Two Hawks, at 22, a promising young hunter whose opinions influenced his peers, openly criticized the waste of valuable hides on unproven modifications. Gray Eagle, responsible for coordinating fuel supplies for their section of the winter camp, warned that experimentation during harsh weather preparation bordered on recklessness that could endanger not just Redman's family, but neighbors who might need to provide emergency shelter. By the final week of November, as other families completed their standard Tipi installations and began stockpiling fuel for the winter months ahead, Redman worked alone on his liner system while enduring increasingly pointed comments about his stubborn pursuit of unnecessary complexity. The conventional wisdom that had guided Lakota winter survival for generations seemed both proven and practical, while his modification appeared to violate the fundamental principle of conservation that governed all aspects of Plains life. Yet his measurements from the initial test on November 30th, when outside temperatures reached 6 degrees below zero and his liner system maintained interior temperatures nearly 20 degrees warmer than neighboring Tipis, suggested that his understanding of heat flow and moisture control might transform winter survival for anyone willing to invest the extra materials and labor required for proper installation. The polar front arrived without warning on December 21st, 1865, transforming the northern plains landscape into a killing field of wind and snow that would test every shelter system across the winter encampment. Atmospheric pressure dropped rapidly as Arctic air masses collided with warmer southern flows, generating sustained winds of 35 to 40 miles per hour, with gusts reaching 60 miles per hour. Within 12 hours, temperatures plummeted from 10 degrees above zero to 20 degrees below zero, creating wind chill conditions that could freeze exposed flesh in minutes. Redman's liner system responded to the storm conditions in ways that contradicted every expectation his critics had voiced. As wind velocity increased, the air gap between outer cover and inner liner created a Venturi effect that actually enhanced the convection current carrying warm air upward. Instead of the gap collapsing under pressure or allowing heat loss as opponents had predicted, the system drew more efficiently, pulling moisture-laden air from the living space and venting it through the smoke hole opening. The visible evidence appeared in fine snow particles that entered beneath the outer wall at ground level, traveled upward through the 4-inch gap, and exited at the apex without ever entering the interior living space. Temperature measurements during the storm's peak revealed the liner system's thermal performance under extreme conditions. While exterior temperatures held steady at 20 below zero, with wind chill approaching 50 below, the interior space maintained 32 degrees at floor level and 45 degrees at 4 feet above ground. These readings represented a temperature differential of 52 to 65 degrees between interior and exterior conditions, achieved while consuming only 30 bundles of dried buffalo dung and 2 4-foot logs over a 24-hour period. Neighboring Tipis using standard single-wall construction recorded interior temperatures of 10 degrees at floor level and 18 degrees at standing height, requiring 45 bundles plus 3 logs to achieve those marginal results. The physics of heat transfer revealed why the liner gap performed better under storm conditions rather than worse. Single-wall tipis experienced direct conductive heat loss through the hide covering, which became increasingly efficient as temperature differentials increased. Wind pressure against the exterior surface created flex patterns that pumped interior air outward through seams and connection points. Most critically, the cold exterior surface became a condensation point for interior moisture, creating frost deposits that further reduced insulation values and created thermal bridges conducting heat directly to the outside environment. Redman's system interrupted these heat loss mechanisms through multiple pathways. The air gap provided insulation equivalent to roughly 11 R value in modern terms, while the convection current prevented moisture from condensing on interior surfaces. The inner liner remained at nearly room temperature because it never contacted the cold outer wall, eliminating the thermal bridging that plagued single-wall designs. Wind pressure against the exterior actually improved system performance by increasing the draft that pulled warm air upward through the gap, creating a passive heat recovery ventilation system that removed moisture before condensation could occur. Two hawks arrived at Redman's Tipi entrance on the storm's second day, his standard shelter suffering from wall flex that allowed wind-driven snow to accumulate inside the living space. The young hunter discovered interior conditions that challenged his understanding of heat and airflow dynamics, while his own tipi required constant fire tending to maintain barely survivable temperatures. Redman's family worked comfortably in single-layer clothing, with his sons sleeping under individual buffalo robes rather than the multiple layers required elsewhere. The fuel efficiency meant that Redman could maintain consistent heat output without the constant gathering and feeding cycle that exhausted families in standard shelters. The storm's duration exposed fundamental differences between survival and comfort during extreme weather events. Families in conventional tipis entered a defensive mode focused on preventing heat loss through behavioral modifications, huddling together, minimizing movement, reducing cooking activities, and accepting interior temperatures that hovered just above the threshold for hypothermia. Redman's family maintained normal daily routines, including food preparation, equipment maintenance, and social activities that would have been impossible under standard conditions. White Cloud continued hide-working projects that required manual dexterity, while their sons engaged in games and learning activities rather than focusing solely on staying warm. The social dynamics within the camp shifted as the storm extended beyond normal duration expectations. Elder Sitting Bear visited Red Man's shelter on December 23rd, ostensibly to check on their welfare, but clearly seeking to understand how the liner system achieved its results. Gray Eagle arrived with questions about fuel consumption rates, having noted that Red Man's family showed no signs of rationing their wood and dung supplies, despite using smaller quantities. The systematic performance advantages became impossible to dismiss as lucky circumstances or seasonal variations. By December 26th, when wind speeds finally decreased and temperatures moderated to 0 degrees, the liner system had demonstrated measurable superiority across multiple performance categories. Fuel efficiency averaged 30% better than standard Tipis. Interior temperatures remained 15 to 20 degrees warmer. Moisture control eliminated the frost accumulation that plagued neighboring shelters, and structural integrity showed no compromise despite wind conditions that had caused minor damage to several conventional designs. Most significantly, the occupants had maintained physical health and morale levels that positioned them better for the extended winter conditions that lay ahead. The storm's aftermath revealed the broader implications of Red Man's innovation for winter survival strategies. Standard approaches that worked adequately during normal weather conditions showed dangerous vulnerabilities when conditions exceeded historical parameters. The liner system's performance suggested that traditional methods could be enhanced through careful observation of natural phenomena and systematic testing of modifications, without abandoning the fundamental principles that had sustained plains cultures for generations. The question facing the winter camp was whether other families would adopt proven improvements or maintain conventional practices based on cultural precedent rather than measurable results. The deep freeze that settled over the northern plains on January 2, 1866, established weather patterns that would persist for 44 consecutive days, creating survival conditions beyond the experience of the oldest tribal members. Daytime temperatures failed to rise above 5 degrees below zero, while overnight lows reached 30 degrees below zero, with sustained winds generating chill factors approaching 50 degrees below zero. Snow accumulation reached 24 inches by January 20th, with drift formations exceeding 4 feet in height around shelter structures throughout the encampment. Standard Tipi construction revealed critical failure modes under extended extreme conditions that brief storms had not exposed. 7 of the 15 conventional shelters developed frost crystal formations on interior wall surfaces, beginning as thin deposits that gradually accumulated into ice layers, nearly 1/8 of an inch thick. These frozen moisture deposits created thermal bridges that conducted interior heat directly through the hide walls to the exterior environment, while simultaneously reducing the flexibility of the hide materials and creating brittle points vulnerable to tearing. The condensation cycle accelerated as interior humidity from cooking fires and human respiration contacted increasingly cold wall surfaces, creating feedback loops that steadily degraded insulation performance. More dangerous than heat loss, the standard shelters began experiencing reduced air circulation as families sealed door openings and other potential draft sources to conserve warmth. 2 families reported symptoms consistent with carbon monoxide exposure, including dizziness, headaches, and disorientation that indicated incomplete combustion products were accumulating in their living spaces. The traditional balance between ventilation and heat retention, calibrated for normal winter conditions, proved inadequate when exterior temperatures created pressure differentials that disrupted normal airflow patterns. Red Man's liner system demonstrated its most significant advantages during extended cold exposure rather than acute storm events. The convection current between outer wall and inner liner operated continuously, powered by the temperature differential between interior and exterior environments. As outside temperatures dropped lower, the draft effect actually increased, pulling more efficiently through the gap, and removing moisture before condensation could occur on any interior surface. The inner liner remained consistently dry and flexible, maintaining its insulation properties throughout the extended freeze period. The fuel consumption differential became pronounced over weeks rather than days of operation. Redman's family averaged 28 bundles of dried buffalo dung daily, totaling 1,232 bundles plus 40 logs over the 44-day period. Comparable standard Tipis required approximately 1,815 bundles plus 62 logs, representing a fuel savings of 32% while achieving superior interior conditions. This efficiency translated directly into reduced labor requirements for fuel gathering, wood cutting, and fire maintenance activities that exhausted families struggling to maintain adequate heat in conventional shelters. Physical health outcomes provided the most compelling evidence of the liner system's effectiveness during extended exposure. Redman's sons maintained normal activity levels and showed no signs of cold-related stress, while neighboring children began exhibiting symptoms of prolonged cold exposure, including reduced appetite, increased susceptibility to respiratory infections, and behavioral changes associated with chronic discomfort. 2 children in standard Tipis, ages 6 and 8, developed frostbite injuries to fingers and toes by January 19th, requiring treatment with warm compresses and herbal remedies that consumed additional fuel resources for heating water and maintaining treatment temperatures. The systematic performance advantages extended beyond mere survival to enable productive activities that would have been impossible under standard conditions. White Cloud continued intricate beadwork and hide preparation tasks that required manual dexterity and sustained concentration. The stable interior environment allowed for food preparation techniques, including slow cooking and drying processes that required consistent low heat over extended periods. Storage of tools and equipment remained problem-free because the moisture control prevented condensation that could rust metal implements or damage organic materials. Elder Gray Eagle documented the camp's fuel consumption patterns throughout January and February, recording data that would influence winter preparation strategies for subsequent years. His measurements confirmed that liner-equipped shelters consistently used 25 to 35% less fuel while maintaining interior temperatures 8 to 12 degrees warmer than conventional designs. The most significant finding was that fuel efficiency improved rather than degraded as exterior temperatures dropped, suggesting that the liner system's performance advantages increased under the most challenging conditions. Two Hawks began modifications to his own shelter in late January, installing a partial liner system using hides borrowed from Redman's surplus materials. His initial results showed immediate improvement in interior comfort and fuel efficiency, though the improvised installation lacked the precision of Redman's carefully planned system. The young hunter's experience provided practical insights into installation techniques and demonstrated that the liner principle could be adapted to existing structures without complete reconstruction. The extended freeze also revealed the psychological advantages of maintaining comfortable interior conditions during extreme weather events. Families in standard Tipis developed patterns of minimal activity and social isolation as they focused entirely on heat conservation and survival. Redman's family continued normal social interactions, storytelling sessions, and cultural activities that maintained morale and community connections during the most challenging portion of the winter season. Children in the liner shelter showed no signs of the irritability and depression that affected youngsters in less comfortable environments. By mid-February, the sustained performance of Redman's innovation had shifted community opinion from skepticism to serious interest in adoption. The measurable advantages in fuel efficiency, interior temperature, structural integrity, and occupant health could no longer be dismissed as seasonal variations or lucky circumstances. The liner system had proven its effectiveness under the most extreme conditions the Northern Plains winter could deliver, establishing a new standard for cold weather shelter performance that would influence tribal construction practices for generations to come. The atmospheric disturbance that struck the Northern Plains on February 16, 1866, combined multiple weather systems into a single catastrophic event that would be remembered as the most severe winter storm in tribal oral histories. A fast-moving low-pressure system collided with stationary Arctic air masses, generating 12 inches of snow within 18 hours, followed by sustained winds exceeding 70 miles per hour. The temperature differential between the storm system and existing Arctic conditions created a precipitous drop from 15 degrees below zero to 40 degrees below zero within 12 hours, establishing wind chill conditions approaching 70 degrees below zero that made any outdoor exposure potentially fatal within minutes. The structural failures that occurred across the winter encampment revealed the absolute limits of conventional Tipi design under unprecedented load conditions. 9 of the 15 standard shelters experienced pole displacement as wind forces exceeded the engineering tolerances of traditional lodge construction. The tripod foundation systems, designed to withstand normal winter winds of 20 to 30 miles per hour, began shifting under sustained pressure that approached double those parameters. Hide covers stretched beyond their elastic limits developed tiers along sewn seams, creating openings that allowed wind-driven snow to penetrate interior spaces directly. 3 families reported complete structural collapse, requiring emergency evacuation to neighboring shelters within the first 24 hours of the storm. Red Man's Shelter became the de facto emergency refuge center as neighboring families sought protection from failed conventional designs. Greyhawk, the 67-year-old elder from an adjacent lodge, arrived on February 18th after his own shelter's cover tore along a 12-foot seam that could not be repaired under storm conditions. Two Hawks brought his wife and infant son after their teepees' supporting poles shifted, creating a dangerous lean that threatened complete collapse. By February 19th, 12 people occupied Red Man's liner-equipped shelter, testing the system's capacity under maximum load conditions that far exceeded its original design parameters. The thermal performance under extreme occupancy demonstrated the liner system's scalability for emergency conditions. Despite housing 3 times the intended population, interior temperatures stabilized at 18 to 22 degrees below zero overnight, rising to 38 to 42 degrees during peak fire output periods. These readings represented interior conditions 50 to 60 degrees warmer than exterior ambient temperatures, achieved while the shelter accommodated bodies that would have overwhelmed any standard teepee's heating capacity. The air circulation system continued functioning effectively, preventing carbon dioxide buildup or oxygen depletion that could have created life-threatening conditions with so many occupants in a confined space. Fuel consumption during the emergency period revealed the efficiency advantages that made extended occupancy possible. Red Man's Shelter consumed 160 bundles of dried buffalo dung plus 8 logs over the 7-day crisis period, averaging 22.8 bundles daily, despite supporting 12 individuals. Standard calculations for conventional teepees, housing equivalent populations would have required 40 to 50 bundles daily, meaning the liner system achieved the same thermal results with roughly half the fuel input. This efficiency margin provided the buffer that allowed the shelter to support emergency refugees without depleting fuel supplies that would be needed for the remainder of the winter season. The enhanced structural performance under extreme wind loading demonstrated engineering principles that conventional designs had not incorporated. The liner system's dual wall construction created internal pressure equalization that reduced stress concentrations on the outer cover. Wind forces that would normally cause hide materials to flex and pump interior air outward were absorbed by the air gap, which acted as a pressure buffer between exterior conditions and the living space. The continuous convection current actually utilized wind energy to improve heating efficiency rather than allowing it to compromise structural integrity. The survival outcomes during the storm's peak intensity provided definitive proof of the liner system's life-saving capabilities. 4 deaths occurred in the winter encampment during the February storm, all in standardy. Tipis that could not maintain survivable interior conditions under the extreme temperature and wind combinations. Ages of the deceased ranged from 4 to 61, representing both the most vulnerable populations and demonstrating that conventional shelters had reached their absolute performance limits. None of the occupants in Redman's liner shelter suffered serious cold-related injuries, frostbite, or hypothermia. Symptoms, despite being exposed to the same exterior conditions that proved fatal elsewhere in the camp. The psychological impact of maintaining comfortable conditions during a life-threatening weather event created lasting impressions that would influence tribal adoption of the liner method. Greyhawk, who had initially dismissed the innovation as wasteful complexity, experienced firsthand the difference between survival and comfort during extreme conditions. The elder's public acknowledgement on February 23rd carried significant weight with other tribal members who had witnessed his traditional approach to winter preparation. 2 Hawks, whose own shelter failure had forced him to seek refuge, became an advocate for liner adoption based on direct experience rather than theoretical arguments. The community response to the crisis marked the turning point in acceptance of Redman's innovation from individual experiment to proven survival technology. Elder Sitting Bear's formal statement at the tribal gathering represented official recognition that conventional methods had reached their performance limits under changing environmental conditions. The systematic documentation of fuel efficiency, structural integrity, thermal performance, and survival outcomes provided measurable evidence that could guide future winter preparation strategies. The liner system had not only survived the ultimate test, but had enabled a single shelter to serve as a community survival center, saving lives that would have been lost to the inadequacies of conventional design approaches. The February storm established Redman's innovation as essential survival technology rather than optional enhancement, transforming tribal attitudes toward winter shelter construction and validating the principle that careful observation of natural phenomena could improve upon traditional methods without abandoning their fundamental wisdom. The transformation of tribal winter shelter practices began immediately following the February crisis, as families throughout the encampment recognized that conventional methods had reached their operational limits under the extreme conditions that were becoming more frequent on the northern plains. By March 10th, 8 of the 15 lodges in the winter camp had committed to liner installation before the following winter season, representing a fundamental shift from individual innovation to community-wide adoption of proven survival technology. Redman found himself serving as technical advisor and construction supervisor for modifications that would affect more than half the families in their band. The installation process required systematic transfer of knowledge that had previously existed only in Redman's experience and observation. Each liner system demanded precise measurements and material selection that could not be approximated without compromising performance. The hide selection process alone required expertise in evaluating thickness consistency, flexibility retention after processing, and edge-seaming techniques that would maintain structural integrity under the stress loads generated by wind pressure and thermal cycling. Redman established standards calling for hides of minimum 4 mm thickness, with no thin spots or previous repair patches that might create failure points during extended use. The construction methodology evolved through trial installations that revealed critical details not apparent during Redman's original development work. Suspension point placement required mathematical precision to maintain consistent gap spacing around the entire circumference, with attachment heights varying by specific degrees to accommodate the teepee's conical geometry. The bottom edge sealing technique proved particularly challenging to replicate, as improper overlap with floor mats created draft paths that negated the thermal advantages, while excessive overlap restricted the airflow needed for proper convection circulation. Redman developed a measuring system using marked sinew lengths and standardized knot spacing that allowed consistent installation across different lodge sizes. Two Hawks emerged as the most skilled adopter, applying the systematic approach he used in hunting to master the technical requirements of liner construction. His installation achieved performance metrics within 5% of Redman's original system, demonstrating that the technology could be successfully transferred to other practitioners with appropriate instruction and attention to detail. Gray Eagle's adaptation incorporated modifications for his larger 20-foot diameter Tipi, requiring proportional adjustments to air gap spacing, suspension heights, and bottom edge sealing that tested the scalability of the liner principle across different structure sizes. The performance data collected during the following winter of 1866 to 1867 validated the widespread adoption decision through measurable results across multiple installations. Fuel consumption across the 8 liner-equipped lodges averaged 30% below previous winter usage, with interior temperature improvements ranging from 10 to 14 degrees compared to standard construction. Most significantly, health outcomes showed dramatic improvements, with 0 cases of frostbite injuries, respiratory infections, or cold-related complications among families using liner systems, compared to 6 serious medical incidents in the 7 lodges that maintained conventional designs. Visiting Cheyenne hunters arrived at the winter camp in late November 1866, seeking trade opportunities, but remaining to study the liner technology after observing its performance during an early cold snap. The delegation included experienced lodge builders who documented construction techniques and adapted the system for Cheyenne teepee designs that utilized different pole arrangements and hide preparation methods. Their adoption represented the first intertribal transfer of the innovation, establishing precedents for knowledge sharing that would accelerate distribution across the Northern Plains tribes. Archaeological evidence from later decades confirms the widespread adoption and refinement of liner systems throughout Lakota winter camps. Museum collections include documented Tipi liners from the 1870s and 1880s, showing construction details consistent with Redman's original design principles while incorporating regional variations and material adaptations. The National Museum of the American Indian houses specimens collected from North and South Dakota sites that demonstrate the technical sophistication achieved through decades of refinement and optimization. Modern reconstruction projects conducted by wilderness survival specialists have validated the thermal performance claims documented in tribal accounts of liner system effectiveness. Field testing under controlled conditions confirmed interior temperature differentials of 12 to 15 degrees Celsius compared to single-wall designs when exterior temperatures reached 20 degrees below 0 Celsius. Wind tunnel testing demonstrated the convection principles that Redman had discovered through observation, showing consistent airflow patterns that removed moisture while maintaining thermal barriers. The scientific principles underlying the liner system's success reflected sophisticated understanding of heat transfer mechanisms, air circulation dynamics, and moisture control that paralleled concepts not formally recognized by European engineering until the late 19th century. The air gap provided insulation through trapped air layers, while the convection current created passive ventilation that prevented condensation without compromising thermal efficiency. The system essentially functioned as a heat recovery ventilator that used natural draft to maintain air quality while preserving warmth. Redman's innovation established design principles that influenced not only immediate tribal adoption, but provided foundational concepts for modern cold weather shelter engineering. The dual wall construction with controlled air gaps became standard practice in high performance winter tents, while the convection based moisture control system appears in contemporary Arctic expedition shelters and emergency survival equipment. His systematic observation of natural phenomena, willingness to challenge conventional approaches, and methodical testing of modifications demonstrated problem-solving methodologies that transformed survival technology through practical application of scientific principles. The legacy extended beyond technical achievements to establish precedents for innovation adoption within traditional societies, showing how individual experimentation could enhance rather than replace inherited wisdom when guided by careful observation and systematic testing of measurable results.